Our last section is about electrolysis and electrolytic cells. Electrolysis happens when you force a current through your cell. You end up with a negative cell potential. So since the cell potential is negative, that means that this reaction is non-spontaneous. That means this reaction does not occur naturally and you have to really force it to happen. You're going to see that forcing in the fact that you're passing electricity through these reactions. That's the name electrolysis. So we're going to look at two examples of electrolysis. We're going to look at electroplating. We're going to look at electrolysis of water. With electroplating, you force a current through this reaction and the ions start to move towards your cathode. Your cations move towards your cathode, and they start to plate on top of the cathode. Right? So if you have something like a silver spoon, this weird looking thing here is a spoon, and you put it into an electroplating chamber, you put a silver bar over here, and you force a current through, the silver ions will move over to the silver spoon and start to plate on the silver spoon because the silver spoon is acting as a cathode. Remember that cathodes tend to gain mass when the cations start adding to them. And then electrolysis of water is one of the most important electrolysis reactions. You really, really, really need to know it. Be sure you know the reaction for the electrolysis of water. I have an electrolysis generator I'm going to show you in class, but pretty much what you do is you have two wires. The wires act as your anode and your cathode. You hook it up to a voltage source, you turn it on and pump electrons through it. When you pump electrons through it, it causes the oxidation and reduction of water, and you form hydrogen gas and you form oxygen gas. Notice that you form twice as much hydrogen as you do oxygen. That's because you make twice as much hydrogen as you do oxygen in your balanced chemical equation. It's important when you do this that in your solution here, you have some sort of ions that will move. If you don't have ions, this won't work. So if you have DI water in here, it's not going to work. If you dump some salt in that water or anything else that dissociates, then you're going to have a real nice electrolysis of water happening. When looking at electrolysis or electroplating reactions and trying to figure out what's going on, your most easily reduced metals, the ones at the top of your chart, are the ones that are going to get plated first. Most electrolysis reactions, you do the problems exactly the same way as you do a regular galvanic cell reaction. The main thing to keep in mind is that your E cell is going to be negative instead of positive since it's a non-spontaneous reaction. Now this next section is about figuring out if you run an electrolysis reaction or an electroplating reaction for a while, how much stuff do you plate on or how much gas do you make? You use this process right here to do this, stoichiometry of electrolytic process. The first thing you're going to do is you're going to take, what it's going to give you is going to give you current, and it's going to give you time. It's going to say you run 20 amps of electricity through this for 10 minutes. And if it gives you current and it gives you time, you can use that to find charge because current is equal to charge divided by time. I is current, Q is charge, and T is time. And so if you multiply the current, which is measured in amps, by the time, you're going to get the total charge. Once you have the charge, you can change the charge into moles of electrons by using Faraday's constant. Once you have moles of electrons, you can change from moles of electrons to moles of the substance by using a mole-to-mole ratio. And then you can go moles to grams by using the molar mass. So let's take a look at an example problem. We are wanting to calculate the grams of aluminum produced in an hour by the electrolysis of a molten aluminum chloride if the electrical current is 10 amps. So I'm going to take my 10 amps and I'm going to multiply it by the time, but my time is measured in hours and I need it to be in seconds, so I'm going to change that to seconds. So when I do this, I get about 36,000 coulombs. Now once I have coulombs, I can use Faraday's constant to change this to moles of electrons. Okay, so here's Faraday's constant. That allows me to change to moles of electrons. And now I can use moles of electrons to change to moles of whatever it is I'm talking about. I'm talking about aluminum. Aluminum has a positive 3 charge. That means that I'm losing 3 moles of electrons per every mole of aluminum. Or, no, I think I'd be gaining electrons. So I have 3 moles of electrons for every 1 mole of aluminum. And now that I've got moles of aluminum, I can change grams of aluminum by using molar mass. And if I go through and solve this, I get about 3.36 grams of Al. Now these types of problems are very, very, very common. They show up on both free response and they even show up on multiple choice. So make sure that you have a grasp on the process, and if you've got that down, then you'll probably do fine. Let's take a look at another example. Now in this one, it gives us amps, it gives us time, it gives us how many grams of metal is deposited, and it wants us to find the molar mass. Well, if it wants us to find molar mass, I need mass and I need moles. And I have mass, so really all I've got to find is moles of the metal, and then I'll have molar mass. So I'm going to start with my amps and my time, and I'm going to multiply those together to get my current, my charge in coulombs. Okay, so I take my time, my 35 minutes into seconds, multiply that out. I got 5,250 coulombs. And now I can plug this in using Faraday's constant to get moles of electrons. And to figure out moles of electrons, we're going to have to think a little bit. It gives me the formula that it forms with nitrate, MnO3 That means the charge on it was positive 2. That means that it lost 2 electrons. And so this will allow me to solve for moles of M. And if I take this and take mass and divide it by moles, I'll get molar mass. And I get a molar mass of about 113.3. If I look on my periodic table, I want something that has a molar mass close to that also has a charge of plus 2. And cadmium looks like my best bet. The last thing that we're going to look at is how to calculate kilowatt hours of electricity. They throw this in once in a great while, so we'll just kind of toss it in here and make sure you've seen it at least, but this is not the most important thing to know how to do. A kilowatt hour is an energy unit, like joules is an energy unit, and if you look here, you see the conversion between kilowatt hours and joules. It's not something you need to know. Now it gives me the mass of aluminum that was produced, and it also gives me the voltage, which voltage is the electric potential. And I can kind of treat this backwards from what we did before. I can take kilograms of aluminum, go through that whole conversion process we did before to get to coulombs, and I get 1.07 times 10 to the 10th coulombs, which is the charge of this. Now this charge is equal to the number of moles that has been transferred, number of moles of electrons that has been transferred, times Faraday's constant. In other words, it's that little part of our equation right there. So if I take this number and multiply it times my potential, which is the same thing as voltage, I will get the work, the maximum amount of work that can be done here. And this work that I would be calculating would be in joules. And so if I want to change this to kilowatt hours, I just divide this by the 3.6 times 10 to the 6 constant that was right here. And I'm going to get somewhere around 1.34 times 10 to the 4th kilowatt hours. So again, this is not that big of a deal to figure this out. Nothing here you need to have memorized that you haven't already had memorized. It's just kind of using the conversion backwards a little bit. And that is it.